Hello all. This lecture is going to continue our trend towards finding more advanced techniques in machine learning and illustrating how they can be used to materials design. That is, stepping away from the conventional, I have a property, I have a structure, and I want to predict a mapping that goes between the two, to moving towards more complicated ways of using those supervised learning techniques to do other kinds of useful tasks in materials design. And in particular, today we're going to look at reinforcement learning and how it can be used to design new molecules. Now, before we get into the mathematics of reinforcement learning, let's take a minute to discuss why one needs to be able to do this in molecular space. And the problem with molecular design is that there are just so many possible molecules that we could evaluate that even considering a brute force search over all these possible molecules with a very fast model, say one that can evaluate 100 molecules per second, it would still take it 30 years to be able to evaluate only the 166 billion molecules that are 17 heavy atoms or smaller. And even within this space of 170 billion molecules, there's still an enormous potential range of functionality such that the kinds of materials that we're looking for, like different kinds of drugs, aren't just clustered in one region of space. So really what it comes down to is how can I search through this enormous space of possible molecules with different structures and different functionalities such that I can find only the ones that are useful for whatever application I have with the least amount of computational effort. In short, we need to find a way to search through this space effectively. Now, one potential route for this is to use reinforcement learning algorithms that build up molecules from scratch. Now, the idea here is well exampled by two papers that came out in 2018 and 2019 out of Google and Stanford that illustrate how one can build an agent that can take a molecule and predict how we modify it such that its properties will improve. Now, the example here illustrated by MultiQN, which is a product out of Google, shows us how we can take a molecule and gradually add atoms and bonds to it such that its properties improve. Here we're measuring the quantitative estimate of drug likeness, or QED. And you can see that this agent not just takes steps that will improve the property, but is also intelligent enough to know when it can take a step that worsens the property, but allows us to access a better space in the end. GCPN also follows this policy of how I can build up a molecule step by step, atom by atom, bond by bond, and both use different kinds of reinforcement learning algorithms that we're going to dig into deep in this lecture. So now that we've defined at least a basis of how these reinforcement learning algorithms are built around some kind of agent, let's talk about reinforcement learning in a more formal sense. Now, reinforcement learning is built around the idea that you have one of these intelligent agents that decides an action to take given its current state such that it changes an environment, and that environment gives it back a new state and a reward for taking that action. And the idea behind reinforcement learning is we want to learn a policy, here expressed by pi, where this policy predicts the kind of frequency with which you should choose an action, or a probability that that action is the best one, given some state, such that this policy optimizes the amount of rewards that we receive over time. And the interesting part about reinforcement learning is that you can't really just measure a policy. Okay, I did put an asterisk on that. You can measure a policy if you've got a really good expert to train off of, but that isn't always the case. And indeed, even if it is the case that you assume humans are good at the policy, you can always do better by kind of gathering experiences on your own. So that aside, the big challenge in reinforcement learning is again that we can't measure a property, or a policy. But what we can measure are rewards for enacting a policy or choosing a certain action in a certain state. And this is something that we can gather by, say, taking a current policy and running it over many different states, choosing many different actions over the course of what are called episodes, where you, say, replaying environment starting from a certain point, like playing a game of checkers from the initial board, and then gathering enough of these rewards, actions, and state pairs that you can potentially start to see the effect of different policies on an environment. Okay, so now that we have this data, we've got a new problem. How do we take these measurements of what a policy does and be able to back out an optimal policy? And that's where a rich field of different kinds of algorithms come into play. And the one we're going to talk about first is a relatively simple and old method called policy gradient. Where here, my goal is to take a policy where, again, I'm using that pi notation where I define the probability of choosing a certain action given a state. That's parameterized by a set of parameters theta, such that this policy will choose good actions more often. And the way that I can do that is by taking my current parameters and updating them based on, one, the gradients of my policy predictions. Here I'm looking at my log probability of choosing a certain action given a state, and multiplying that by a value where positive values are good, negative values are bad. And you can see that, all right, if I have a positive value, I'll move in the direction of the gradient that makes my probability of choosing that action more favorable. And if that's negative, I'm going to step in the opposite direction, towards the negative of the gradient. Now, action and state are things that we can measure directly, but this value is something that we have to derive from the rewards, which are, again, something we can actually measure. And the idea for getting the value of a state is we sum up the rewards of all of our future states, looking towards some time horizon of n possible steps, and multiplying them by a weighting factor, such that we get, say, more benefit for choosing rewards very close to my current state t, which gives me a value for that state. And then I subtract off the average reward that I find for, say, a certain amount of states, and that gives me my positive value for states that are above average value, and a negative for those who are worse than average. And that goes back to here and gives me my property v, such that v is positive for good actions, which again make me step in the direction of moving my parameters such that it increases the probability of that action, or when it's negative, moving away from that direction. Now this can get a bit more sophisticated, and we can indeed fix one of these problems that here I'm operating under a fixed time horizon, and this is going to break down if, say, my really good rewards are only really visible if I hold out for a very long time. So one thing I can do is, say, using an actor-critic model that lets me look infinitely far into the future. And it follows a fairly similar tone, where I've got my, here's my gradient term, where I want to step in the direction according to the probabilities of that state in action, multiplied by this Q function, where this Q function here is called the critic term, where my policy function is called an actor, and it's called the critic because it weighs the values of my moves. And this is a function that's dependent on the states and actions, which are things that I can measure, and it's trained based on the reward. So the way that we do this is we update our critic function at each step based on some time-dependent error of the predictions of the value of its property. And this is using a term called the Bellman equation. We're not going to go much into today, but what it does is it gives me an error of describing how well my estimate of the value of a certain state is by comparing it to the actual value of what we observe for choosing that action and moving to the next state, where I can estimate that reward by taking the reward that I have and then adding some time-dependent term that looks at my value of the next state. So if you can recall back to our previous slide where we showed this whole idea of I discount future rewards by this parameter gamma, and I sum them up through a fixed horizon, here I'm doing so inductively. I look at one step and I update its value according to the predicted value of the next step, and that's kind of bumping this value of my current state towards the value of that next state. So it's kind of like taking my rewards from the future, which I can estimate, and trying to correct how well those estimates are. And so once I have that, I've got a ability to express my error in how much this parameter was off, and I can update the weights for this Q model. So again, if I can look at both my measurements of what direction changing my actor would be, what direction changing my parameters theta for the actor would be, I can move them towards the direction that will give me higher Q values by continually updating my Q values, which are again my new way of predicting the future reward, by continually updating that prediction of future rewards by gradually correcting it with the observed reward for taking a certain action this here. So these are just two methods from a rather rich field of reinforcement learning. We're going to go through a few more in our practical exercises and show you kind of a deeper set of the math on how they work. But really the one thing I want to emphasize here is that this is a field with decades of history and a 500-page textbook. So there's still a real rich set of information you can learn about reinforcement learning. But these two techniques here, this policy gradient and actor-critic, hopefully express the ways that you can learn a policy through some simple methods. So that aside, we're now going to talk about how we can use these models in practice. And here we've got really several independent choices to make, or several somewhat independent choices to make. The first of which is, what training algorithm am I going to use? And that is, how am I going to express a policy? What functions do I need to define? And how am I going to learn them? So this could perhaps be choosing between policy gradient and actor-critic. The second is to choose how we're going to express the environment to represent the scientific problem we're trying to solve. And then finally, how can I take those representations for a state and action that I chose for the environment and use them to create learnable functions that are needed by our training algorithm? So to actually give some picture about what that means, we're going to go into some of those algorithms that I alluded to earlier and explain how they work. We're going to start off with MolDQN, which was a paper from just 2 years ago. And they use a third method for training a machine or a reinforcement learning model called deep Q learning. So the idea is that the Q function defines the value of a certain action at a certain state. You can remember it from that actor-critic, where I can take the action that gives me the best Q at a certain state, and that should define our optimal policy. So this is the one function that we need to have in order to define our policy. And we learn it using that look-ahead or Bellman equation approach that we described earlier, where I look at my observed value for moving to the next state, given a certain state and action that were chosen, and I express that state's value by looking at the reward that I observed and then adding in some value that's equivalent to the predicted next state. And then by gradually correcting this value, I've got a loss that defines me, well, what was the value that I thought would be at a certain point, and then what can I estimate for what it actually should be, which is again the reward that I observe plus an estimate of my future rewards. And if I do that enough times, I can inductively learn what my reward for choosing a certain action in a certain state would be. Now the way that they define their environment is to have a function where I describe my state to be a molecule and my actions being possible changes to that molecule, like adding an atom, like a oxygen that's double bonded onto a ring, or by adding a bond within a loop, or removing it. And given that I have my state in action, and because I've chosen deep Q learning, what I need to define is this Q function that again takes my state in action. My next function is, or my next step is, how do I create that functional form? So I can tell you immediately, the one thing they don't do is represent that function by taking, say, a description of that current molecule and that action that we would take separately, because that's rather difficult. We've discussed different ways of representing a molecule graph earlier, which could be things as, say, simple as computing descriptors of it, using Mordred, or other kind of chemoinformatics packages, or taking fingerprints. That one's easy. But capturing what an action is very difficult if it could be, say, a bond addition, or a deletion, or adding an atom, because they're all very different physical properties. So that would be a very difficult problem. But what Zhu and others decided to do instead was to realize that because Q in learning takes a state in action, and even though in many systems that are, say, probabilistic, those choosing a certain action in a certain state doesn't always give you the same result, it is for molecule design. Taking a specific action and applying it to a molecule always yields the same next molecule. So what they chose to do is describe their state and action pair as what the resultant state should be, which is, again, an entire molecule, and that is an easy task. And what they chose to do was compute fingerprints. Morgan fingerprints are a method that's easily available and works for a lot of problems. And they can take that fingerprint for the molecule and pass it through a deep neural network to be able to express how a new state is related to its Q value. So again, what this shows is how they can take a state and an action and use them to create a machine learning model that can predict the Q of the next state. So moving on from here, we'll talk about another method for molecular reinforcement learning, which is the Graph Convolutional Policy Network, or GCPN, which came out of NeurIPS in 2018. So here they're using another version of the policy gradient that we learned earlier that has a few different characteristics to it. Instead of learning a Q function to define the value of a move, they use the so-called advantage, which is defined by looking at the values of moves in advance. They also use a clipping function to ensure their policy doesn't change too much between steps. They also use this conservative function where they say normalize the amount of change that's going to occur by how probable we thought this move was going to be in the first place. And this gives us two different functions that we have to learn. This value function that takes a state and expresses its value, and again our policy function, which takes an action and a state. The environment is very similar to the one from MoldDQN, where their state is a molecule, but they have a different set of actions, where their actions define what bond we should be adding to this network. And here I define my action as picking a first atom to connect, a second one, the type of the edge that we should use, and then finally whether we should add any more bonds after this. And some of the creative things that they did were they were able to represent bond addition using this network by having a collection of disconnected atoms, such that if I predicted my second atom to be one of these disconnected ones, it would add a new bond that adds it to the molecule. And you can see how here you can use that to build up ring structures. I start with 5 linear connected atoms. My first move is to predict adding a double bond to a carbon atom. And then my next move shows how I can add a single bond to the two ends of the chain, and that now gives me a benzene molecule. So here we have to learn two different functions. One is our action function, and here we use graph convolutional networks to express those functional forms, where this gives me the advantage of being able to generate features that are specific to each atom in that molecule. So what I can do is I can take those features and I can pass them through a neural network M, and then a softmax function, which gives me a distribution of values between 0 and 1 for each atom in the network, which I can take to mean probabilities for choosing that as the first atom at the root of a bond. I can then also take those molecules, or those same atom features, and I can build a network that takes the features of my first atom, it takes all of the features of every remaining atom, and predicts a probability that I should choose that atom to be the second bond. I can also represent the edge type by taking the properties of each of the edges, and this goes on through the rest of the network. And my value function, I can just take my atom features, combine them to create a feature that describes the entire graph, and pass that through the readout functions and the neural network output, just as we've discussed in the earlier lecture on message passing neural networks. So these have shown two different common routes for building molecules that emerged a few years ago, but there have been some additional improvements on them in the future, such as this forward synthesis space policy gradient approach, where instead of allowing any kind of atom to be added, they only allow additions to a molecule that follow known reaction pathways. So what this does is it not only shows you molecules that can basically take on a variety of structures, but by restricting the way that they're developed to following only known reaction routes, this proposes a kind of a candidate synthesis pathway by recreating each of those reaction steps that were used to create the molecule in the first place. And these use of reinforcement learning aren't just limited to molecules. There have been some really clever work out of Denmark where they showed how to build up 3D structures using Q-learning, where they define an environment as the cubes of space around an existing, say, 3D structure, and their Q value, or their Q network, predicts the advantage of adding a atom at a certain point within that structure, which allows you to, say, iteratively build up a surface structure atom by atom. Alright, so that concludes our lecture for today. We've covered both reinforcement learning at a very high level, where we've illustrated how that's a process of learning a policy by interacting with an environment, measuring what action you took in which state and what rewards you received for doing that, and then updating some functions that represent your policy using a variety of different methods like Q-learning, which we discussed with MultiQN, where you learn the predicted future value, which is a term known as Q, for choosing a certain action in a certain state, and you can develop a policy of picking the best ones as a function of time, or you can use tools like PPO or Actor-critic that learn that policy directly, and you can use them for many different kinds of scientific problems if you follow the process of choosing a learning method that you want to use, identifying an environment that can represent how to solve your problem, and then choosing how to take those functions needed by your learning method and use the descriptions of your state and your action to be able to build up a network. And again, to recap, MultiQN does this by representing your state and your action, which are needed by the Q function, as the resultant molecule that they would produce. So that wraps up our discussion for today. This is a very math-heavy subject, so I'm going to strongly encourage you to go through the notebooks that illustrate the fundamentals behind policy gradient and Q learning that'll be available along with this lecture, and I should be recording a video that goes through those methods in more detail to correspond with those notebooks.